This is section 10.1, lines. So in this section we're going to talk about conics. Sometimes they're referred to as conic sections. And basically what a conic is, it's what you get when you cross or intersect a plane with a double set of cones. Okay, and that resulting shape is called a conic. Now in just a second we're going to see what conics have to do with lines, but for now just a general introduction to conics. So the first conic is a circle. This is what happens when a plane intersects a double cone such that the plane is exactly parallel to the base of the cone, of the double cone. So this plane here is parallel to the base of the cone, and it intersects the cone in such a way that the resulting shape is a circle. Now an ellipse is similar. An ellipse is what happens when a plane intersects a cone, but the difference is that the plane is not parallel to the base of the cone, and so we get an oval shape, and that's called an ellipse. With a parabola, we have again a plane that intersects a cone, but notice that in this case the angle is different, and it never does meet the other side of the cone. Notice that for the circle and the ellipse, the plane went in one side of the cone and came out the other, so to speak. Goes in one side, comes out the other. But with a parabola, the plane intersects one of the cones, either the top or the bottom, but it does so at such an angle that this plane will never come out the other side of the cone. So this is the point of entry. We can see where the vertex of this parabola is, but there is no point of exit, as there is with circles and ellipses. And the final conic is a hyperbola. A hyperbola is the result of a plane that is perpendicular to the base of the cone, intersecting the double cone. And as you can see, the bottom curve is exactly symmetrical to the top curve. And that's because this plane is intersecting exactly perpendicular to the base of the double cone. So these are basic conics. We're going to spend most of this chapter talking about parabolas, ellipses, and hyperbolas. But today, this is just an introduction to conics. You've probably seen them before. So this is more of a review than an introduction. And we are going to spend only one day on this section 10.1. Now, what do conics have to do with lines? That's what this screen is about. These three shapes here, or these three geometric figures, are called degenerate conics. Degenerate conics. So a point is the result of a plane that intersects a double cone at exactly the spot where the 2 points of the cones meet. That's a point. A line is a result of a plane that is tangent to the double cones but doesn't go through them. Okay, so we can see this plane is tangent to the bottom cone and it's tangent to the top cone, but it doesn't actually enter or exit the cone at all, as with the basic conics. It doesn't enter or exit the cone. It's simply tangent to it, and it's tangent to it along a line. And finally, two intersecting lines are the result of a plane that intersects and is tangent to the double cone. But as you can see here, we're only looking at the cross section. Okay, when we had a hyperbola, that would be the shape that I guess would be closest to this. When we had a hyperbola, the plane that's perpendicular to the base of the double cone was entering and exiting the double cone at a place where the cone was curved. but with two intersecting lines, that plane is perpendicular, and it intersects the cone at exactly the spot where they meet. So right down the middle, it basically cuts these two cones in half. And so the resulting cross-section would form two intersecting lines. Today we're going to focus on lines, which is the second of the three degenerate conics that we just examined on the screen. So when we're talking about lines, lines have inclination and slope. Now you remember from Algebra 1 that slope is just rise over run. Okay, so that much is not new. But now we're introducing a new term, which is inclination, and you'll see that it's very closely related to slope. It's basically the same as slope, but expressed in a different way. The inclination of a line is the angle theta the line makes with the increasing x-axis. All right, what that means is the following. Let's say this is a line, and I purposely didn't write an equation for the line because I want you to just think in general terms for now. If this is a line, we can see that this line crosses the x-axis, and it makes an angle with the x-axis. Now, by definition, the inclination angle is the angle that the line makes with the increasing x-axis, or the part of the x-axis that lies to the right of the angle. That's the increasing x-axis. And these angles are always measured counterclockwise from that increasing x-axis. So, we start here where the arrow is pointing, and we kind of trace the arc up to the line, and that is our theta. Okay, so the inclination of line is the angle theta that it makes with the increasing x-axis. And with this particular line, let's say that it crosses the x-axis at the point -6, 0, and it crosses the y-axis at the point 0, 5. So the slope m of a non-vertical line is tangent theta. And this just relates slope to inclination. So let me just explain that for a little bit. Notice where my cursor is pointing right now. It's kind of outlining the side that would be considered opposite. If this is a triangle, here that I'm outlining here with the cursor arrow, well then, considering this angle theta, the line opposite to it, the length opposite to it, represents a vertical distance, and the length adjacent to it represents a horizontal distance. So since slope is rise over run, well then my rise is 5 and my run is 6. My rise is 5 and my run is 6, and if slope m is rise over run, then what is the slope of the line above? Well, I'm sure that you can just remember from Algebra 1 that this slope then would be 5 over 6. Rise over run, rise 5, run 6, so 5 over 6 is my slope. Now a little bit harder, what is the inclination? Well, we know just from the drawing that our inclination is theta by definition, because it's the angle that the line makes with the increasing x-axis. So the question is, do I have enough information to find theta? Well, we know that the tangent of an angle, the tangent of this theta, is opposite over adjacent. And the opposite of this theta is 5. The adjacent of the theta is 6. And so opposite over adjacent will give me the tangent. But wait, you're saying, that also gives me m. Okay, well that's the whole beauty of this, is that slope is related to tangent. The rise over run, or m, is the opposite over adjacent of this angle theta. And therefore, if I know the slope, which in this case is 5/6, then I can easily find the theta, because theta equals the arctangent or inverse tangent of 5/6, and that is 39.8 degrees. All right, quick comment about inverse tangents. Now, you may or may not remember this from Algebra 2, but every trig function, the three basic trig functions are sine, cosine, and tangent. And and all three of those have inverses. And the way to read an inverse here, this little part that I'm circling with the arrow, this would be read, the angle whose tangent is 5, 6. Okay? This tan looks like -1, but it just means it's just read tan inverse. The tan inverse, or the inverse tangent of 5, 6. And that means the angle whose tangent is 5, 6 is 39.8 degrees. Now, we are going to cover this a lot more extensively in the next semester. I'm purposely saving trig for the next semester because that'll be closer to the time you take calculus. And you'll be using a lot of trig in calculus. But for now, it's very easy to do this on your calculator. Okay, there is the tan button. You can easily find the tan button. And you'll notice right above the tan button there's an arctan. Some calculators say arctan, some say atan, some say tan minus 1. But there is an inverse tangent function there. And all you have to do is use that button with 5, 6 in parentheses, and you get the right answer. One other little caveat about using calculators, though, is, and you're going to see this a lot with trig, you need to make sure that you're in the right mode. So remember that there are radians and there are degrees. If you are doing a degrees problem, then you want your calculator to be in degrees. So if, for example, you just now punched 5, 6 in using the inverse tan function and got something different from 39.8 degrees, it's probably because you're not in degrees mode. So you can change that in your settings. Again, we're going to go through the math of sine, cosine, tangent, and all the inverse functions in the second semester. For now, you really just need to be able to do it on your calculator and to know that the inverse tangent is simply read as the angle whose tangent is. Alright, the angle between two lines. So the angle theta between two lines is the acute or right angle at their intersection point. Let's say we have one line that has an inclination of theta 1, the angle that it makes with the increasing x-axis. We have another line that has an inclination of theta 2, which is the angle that that line makes with the increasing x-axis. And then there is an acute angle theta between these. Now, again, just to clarify what we mean by an angle between lines. Well, if you look at where the arrow is pointing now, you can see that these two lines intersect at a point. And we can consider two angles. There's an obtuse angle that the two lines make. There's also an acute angle that they make. And so, by definition, the angle theta between two lines is always the acute or right angle. It's not the obtuse angle. Now, keeping in mind what we learned in geometry, we can write this equation. So theta equals 180 minus theta 1 minus 180 minus theta 2. Now where does that come from? Alright, follow the mouse arrow right now. With the mouse arrow, I am tracing a triangle. And we know that the interior angles, the sum of the interior angles of a triangle is always 180 degrees. So to put this, to put theta in terms of theta 1 and theta 2, I need to remember that this angle here that I'm pointing to right now with the mouse arrow is equal to theta because vertical angles are equal. And also this angle here, which is right next to theta 2 and is part of the triangle, this angle here is the supplement of theta 2, and so it equals 180 minus theta 2. So putting all that all together, to figure out what theta is, I need to just subtract the other two angles from 180, since the sum of interior angles of a triangle has to be 180. And so that would be 180, the total for the triangle, minus theta 1, and this is theta 1 here that I'm circling, minus the remaining angle, and the remaining angle is expressed as 180 minus theta 2. This is 180 minus theta 2, which I'm pointing to right now with the mouse arrow. Okay, so this is one of the angles of the triangle, this is the other one, and 180 minus those two gives me the remaining angle, which is theta. So theta then, in terms of theta 2 and theta 1, is simply theta 2 minus theta 1. And that is what happens when I simplify this expression. 180 minus theta 1 minus 180 minus theta 2. Alright, now this is a formula that you're going to need to use. I don't want to go through the full derivation here for two reasons. One is that it might be kind of lengthy and perhaps even confusing. Derivation should clear things up, not make them worse, and I think this derivation might confuse you. And the second reason, and more importantly, is that we haven't really gone through trig extensively yet. I know you were introduced to it last year. We're going to get by with that knowledge for now. And then in the second semester, we'll go more in depth in the trig concepts. So the tangent of theta, and we already showed that theta equals theta 2 minus theta 1. So the tangent of theta equals tangent of theta 2 minus theta 1 equals this expression, tan theta 2 minus tan theta 1 over 1 plus tan theta 1 tan theta 2. Now, since the slope m is the same as tan theta, I can write the expression in this way. It equals the absolute value of m2 minus m1. That's the same as tan theta 2 minus tan theta 1, divided by 1 plus m1 m2, which is the same as 1 plus tan theta 1 tan theta 2. Now, for those of you who are interested in proofs and would like to take the time to go through this, you can do it on your own on page 424. For those of you who aren't interested in the proofs or who just don't have the time for it right now, we will learn why this is true in the second semester. Let's do this example. What is the angle theta between the lines 2x minus y equals 4 and 3x plus 4y equals 12? So this is our line 2x minus y equals 4. And notice how it's just rewritten here in y equals mx plus b form, also known as slope-intercept form. Y equals 2x minus 4 is the same as 2x minus y equals 4. Algebraically, it's the same. And drawing our other line, which is negative 3/4 x plus 3, this is in slope-intercept form, and negative 3/4 x plus 3 is algebraically the same as 3x plus 4y equals 12. Okay, so we've graphed our two lines, and we are asked to find the angle between them. Now, based on what we learned about the definition of an angle between two lines, which angle are we talking about here? Are we talking about this angle, which I'm indicating with the mouse arrow, this angle, or are we talking about this angle, which I'm indicating with the mouse arrow? Which of the two is the inclination angle? Well, I'll give you a second to think about that. And alright, you've had enough time to think about it. You should have said that it was this. Why is it this one? Because this is the acute angle, the angle that's either acute or right between these two lines. We did not choose the other angle because that was obtuse. Alright, so how do we do this? You have the formula, and right now you have enough givens to use it. So pause the video now, do this on your own, and then resume when you have an answer. So the tangent of theta equals the absolute value of m2 minus m1 over 1 plus m1 m2. The tangent theta equals, filling in just the different givens, we know that this m, if I'm calling this my m2, then this would be 2. And if I'm calling this my m1, then this would be negative 3/4. But it really doesn't matter what you call m2 and m1. And the reason that doesn't matter is we can see that here, what I'm circling right now. m2 minus m1 and m1 minus m2 only differ by sign. The absolute value negates that, whatever it's going to be. So we're really only going to talk about the absolute difference here. Then m1 times m2 is the same as m2 times m1 because of the commutative property. So again, it really doesn't matter what you consider m2 and what you consider m1. Okay, so filling in the givens then, I can calculate that tangent theta equals 5.5, and the angle whose tangent is 5.5 is the inverse tangent. So theta equals inverse tan 5.5, and that equals 79.7 degrees. Last example, we're going to find the distance between a point and a line. Alright, so let's say we have a line y equals 2x plus 1, and we have a point 4, 1. And the question is to find the distance from this point to that line. Well, without getting into all the techniques, you know that the shortest distance from this point to this line is going to be a straight line from the point to the line. But not only a straight line from the point to the line, it's also going to be a straight line that is perpendicular to the line. That will give us the shortest distance, which is the true distance. Alright, so intuitively you should see that we're going to be looking for a line segment that's perpendicular to the line y equals 2x plus 1, and that'll be our distance. The strategy for a problem like this: first, find the formula of the perpendicular line. Second, find the intersection point of the two lines. And third, use the distance formula to find the length of the line that connects the 2 points. Alright, so let's go through the first step. The first step, we have to find the formula for the perpendicular line, because we already know that the distance or line segment connecting these will be shortest along the perpendicular line. So we need to find the formula for the line that is perpendicular to our given line. Now, from Algebra 1, you remember that perpendicular lines always have a slope that is the negative reciprocal of a line. Okay, so going through that process, and again, this is just review of Algebra 1. How do I fill in the negative 1/2? Because I know that perpendicular lines are always a negative reciprocal of the other line. Okay, so if this slope is negative 1/2, its negative reciprocal is 2. And if this slope is 2, its negative reciprocal is negative 1/2. So that's how I can fill in the negative 1/2. I'm leaving b as b because that's my y-intercept, and I don't know what that is yet. I have to calculate it. So my second step then is to use the fact that the point 4, 1 lies on the perpendicular line. And so I fill in 1 for y and 4 for x. And then 1 equals negative 1/2 times 4 plus b. With that I can solve for b. And therefore b equals 3. My y-intercept is 3. Putting that together then, the formula for this perpendicular line on which the point 4, 1 lies is y equals negative 1/2 x plus 3. The negative 1/2 is the negative reciprocal of 2, and the 3 is the y-intercept, which I have found algebraically here on the left side of the screen. Alright, so we've done the first step in our strategy. The second step is to find the intersection point of the two lines, and you know enough algebra to do that yourself. Find the point at which these two lines meet, and pause do that and then resume when you have that point. Alright, this is what you should have come up with. The point is 0.8, 2.6. 0.8, 2.6 is the ordered pair. And now we're ready for the third step. Use the distance formula to find the length of the line that connects the 2 points. You should have learned the distance formula in Algebra 1 and reviewed it in Algebra 2, but just in case you've forgotten it, this is the distance formula. The distance formula is simply based on the Pythagorean theorem, because follow what my mouse arrow is doing again. I'm going to trace a triangle. Okay, right now I'm tracing a triangle, just roughly. It's not perfect, but you get the idea. Tracing a triangle, I'm just tracing it over and over again, and we see that with this triangle, the hypotenuse is the distance in question. And I have a vertical leg and a horizontal leg that I keep tracing over and over again with the mouse arrow. Alright, and that vertical leg and horizontal leg relate to the hypotenuse according to the Pythagorean theorem as a squared plus b squared equals c squared. Okay, that's nothing new. And the reason I just went through that, though, is because that explains where we get this distance formula. See, this x1 minus x2, that only gives us, that's just giving us the horizontal leg length. And the y1 minus y2 is simply giving us the vertical leg length. And I square both of those, add them up, and that would give me the hypotenuse squared. But since I'm only interested in the hypotenuse, not the hypotenuse squared, I take the square root of the whole thing. So this is the distance formula. Now pause the video, fill it in, and resume when you have an answer. So you should have filled it in like this: x1 0.8, x2 4. And remember, it doesn't matter which one you consider x1 or x2, because since I'm squaring these differences, I'm negating whatever sign there might be. I'm just, ignoring the sign, so to speak, because the squaring is always positive. Something squared always results in a positive result. So whatever you choose x1 or x2 to be, you're still finding the difference between 4 and 0.8, either 0.8 minus 4 or 4 minus 0.8. And then over here, the vertical difference, 2.6 minus 1 or 1 minus 2.6, however you did it. But you'll end up with the same answer either way, and that is 3.58. So the distance from the point 41 to the line y equals 2x plus 1 is 3.58. Here's the classwork, page 732. Please write these numbers down, and we'll see you in class.